my meat so that I can share the video with you later. Okay. So we're recording the video, and we're going to talk about these chemical reactions that can go in both directions at the same time. So I should be able to get my pen up. Okay, so a few key ideas first of all. So the most important thing today is that we understand that some chemical reactions, when we've learnt about chemical reactions so far, mostly we think, well, substance A reacts with substance B, and then it turns into something different. So say substance D and C and D. Okay, but actually in chemistry, some reactions can go forwards, so we think of to the right as forwards, and backwards at the same time. And we use a special symbol for that, which looks like this. So if I was rewriting my equation up here as a reversible reaction, I might write A reacts with B reversibly to make C and D, and at the same time C and D react and go back to being A and B. So this reaction is going forwards to the right and backwards to the left at the same time. Now you could have different speeds, and we know that reactions can be affected by various factors. So far we've learnt in this topic that, for example, temperature can change the rate of reaction. Concentration of solutions can change the rate of reaction. The pressure in gases could change the rate of reaction. The surface area of solid reactants could change the rate of reaction. And if we've got one, we could use a catalyst, and that would also change the rate of reaction. So these 5 things can affect how fast a reaction happens. Okay, when we're talking about reversible reactions, we could say any of these factors could make the forwards reaction go faster, or could make the backwards reaction go faster, or have no effect. Okay, so if the forwards reaction was going faster, we could think of it like this, and if the backwards reaction was going faster, we could think of it like this. Okay, so if making this chemical reaction here, A and B, if we made it hotter and that favoured the forwards reaction, it would be having the opposite effect on the backwards reaction. If making it hotter makes it go this way, making it hotter slows it down in this way. If making the pressure higher pushes it forwards, then making the pressure higher slows down this reaction backwards. So you can see that if something has an effect in one direction, say forwards, it will have the opposite effect in a backwards reaction. So let's say A and B turn into C and D better if it's hotter. If I want more of C and D, I need to make it colder. Okay, so it can be any combination of these factors, but we need to appreciate that if something makes one direction go faster, it will make the other direction go slower. And here's a key word: if we keep the reactions at a fixed set of conditions, eventually they'll reach a balancing point where the rate forwards and the rate backwards are the same, and we say that the reaction is in equilibrium, balanced, equal. So equilibrium means doesn't mean the reaction has stopped, A and B are becoming C and D, and C and D are becoming A and B. It means that because it's happening at the same rate in both directions at the same time, the relative amount stays the same. So you could think of it as, let's say it's your bank account. If you pay in the same amount of money each month and take out the same amount of money every month, then the amount of money in your bank account at any time will remain constant. Okay, so if you take things out or put things in at the same rate, what's left behind stays the same. Okay, imagine you had a jar full of marbles, yeah, 2 jars full of marbles, and you're moving marbles from one jar to the other jar. Okay, if you do it at exactly the same rate, there'll always be the same number of marbles in each jar. That's what equilibrium means. Okay, now reversible reactions, you know about some already. So an example here is using indicators to test whether things are acid or alkali. We've got some indicator paper here, some litmus paper. Okay, so we should already know that red litmus can turn blue and blue litmus can turn red, and that reaction is a reversible one. Let's look at what this means here. Look at this equation. It looks complicated, but it isn't really. So we should be happy with the fact that if something is acid, then litmus, this chemical, the indicator, is red, and if something is alkali, it is blue. Okay, now this equation here is showing that there's our symbol for the reversible reaction. We already know that if you see that, hydrogen ions are what makes things acid. Remember, the pH scale is measuring the concentration of hydrogen ions, and this reversible reaction here is showing that when the litmus is tagged on with the H, it will be red, and if the H is floating about and the litmus is on its own, it will be blue. So we could make this, if you took this piece of blue here and put it into the acid, it would go red and back to blue and back to red and back to blue. Okay, that's what we mean by a reversible reaction. I'm going to watch a quick video, hopefully. Okay, so this reaction is called the blue bottle reaction, and you'll see why in a minute. I think I can make it play. Come on. Okay, so it doesn't matter about the sound. So you've got this reaction here in this flask. It's clear. Shake it up. Goes blue. Okay, keep watching the blue flask because the reactants in there are doing a reversible reaction. In one direction, the products are blue, and then that set of products are now breaking down and going back to the clear set that they were at the start. And now if we want to show that it's a reversible reaction following it being clear, then we can give it another shake and it should go back to being blue again. Okay, so we've got reversible reactions that go in both directions, and our next thing is to understand what's happening to the energy. So you can see here I'm still representing my chemical reaction with A and B turning into C and D, and at the same time C and D breaking down into A and B. Okay, so look at these definitions on the arrows here. If the reaction transfers energy to the surroundings, in other words, it gives out energy, that would usually be heat. It would be exothermic. And if the chemical reaction is taking in energy, we know the word for that is endothermic. And a key bit of understanding here is that if this is exothermic by a certain amount of energy in one direction, it's endothermic by the same amount in this. So if this reaction, if this example here, when it's going forwards, let's say it gives out 150 kilojoules of energy, if it gives out, if it gets hotter by 150 kilojoules going forwards, then it's going to get cooler and take in 150 kilojoules from the surroundings in the other direction. The size, the value of these amounts of energy is the same. Okay? And it doesn't have to be exothermic forwards. We could equally have a chemical reaction. Let's do E plus F reacts and makes G plus H. It could be endothermic going forwards and exothermic going backwards. But the key thing would be that if this is, let's say this is 300 kilojoules going in from the surroundings, in the other direction, it would give out 300 kilojoules. The amount of energy is the same forwards as it is backwards. In one direction, the energy is given out, exothermic. In the other direction, the energy is taken in, endothermic. Okay, and we're going to use this example here. So you might have come across, or you will have come across, copper sulfate, which is blue, and it's blue if it is hydrated. You could guess what that means. The copper sulfate has got water attached to its crystals. Copper sulfate is blue when there is also water molecules held inside the crystals of the copper sulfate. It makes it look blue. If you roast that blue copper sulfate and heat it, give it lots of energy, we can push the water out and we can turn it into anhydrous, no water, dry copper sulfate if you like, which is white. No water is attached. The water has been pushed away and evaporated. Now this reaction is reversible, and it's also a test for the presence of water. So if you took your white copper sulfate and you added water to it, it would go blue. If you heated up the blue copper sulfate, roasted it with a Bunsen burner, the water would be driven off, it would go white again. Add water back, it goes blue. Heat it up, it goes white. And you could keep doing that because the change is reversible. Okay? Remember what we said about the energy. The blue copper sulfate needs to take energy in by being roasted. It's endothermic going forwards. It's taking in heat. And so if I do the opposite and add water to the white copper sulfate and it goes backwards this way, it goes from white to blue, it gives out energy. Heat it up, takes in energy, goes white. Add water back again, gives out energy, turns blue. And here's a diagram to show that in an energy graph. So here is our blue copper sulfate. And we know that going forwards, it is endothermic. In other words, it's got to take energy in and turn into white copper sulfate up here. The opposite direction is going the other way. The white copper sulfate reacts with water and gives out energy and goes back to being blue. And this value here is the amount of energy. So in our equation, we know that endothermic, taking in, it's going to take in 78 kilojoules of energy, and going backwards, exothermic, it's going to give out 78 kilojoules of energy. Takes in energy from the surroundings and cools down, going forwards, gives out energy, warms up the surroundings, going backwards. All right, so forwards or backwards The amount of energy is the same. You're reversing the reaction, okay? This reaction doesn't stop when you heat up blue copper sulfate and it turns white. The reaction isn't over, because if there's water around, it will go back the other way and turn blue again. Okay, we can encourage the reversible reaction to go forwards by heating it up, because it needs to take in energy when you heat it up, and so heating it up makes it go this way and turn white. Okay, so it's quite tricky ideas here to think about. And now your job is to go back to your exercise book, your textbook, sorry, and have a go at the questions that I've shown you in the assignment. Right, there are 2 other videos which you can watch, and those 2 videos will help you understand these reversible reactions.